Today, we want to talk about integration by a substitution. We want to introduce the concept formally. The goal is to build an intuition about integration by substitution. The goal is to be able to identify quickly what derivatives have been found using the chain rule. When do we have the form f prime of g of x times g prime of x dx? Notice that when we go from f prime of g of x times g prime of x dx, the only thing that we're integrating is f. So notice that when we reverse our chain rule, the only thing that actually gets integrated is the f. What makes this go is the g prime. So the function that we're integrating is f. That's the one that I'm going to be referring to as the outside function. This is a question of observing and how we think about thinking about how we think about things. Notice that f prime is the one that we're actually integrating. That's what we're applying our integration formula to. If f prime is sine, then f is negative cosine. If f prime is e to the x, then f is e to the x. Bad example. If f prime is x squared, then f is 1/3 x cubed. It's the thing that we're actually applying our integration rules to. So we're going to call this the outside, and it's going to be the one that we're integrating. Notice that g prime of x dx is only there because of the chain rule. The g prime is what is going to make substitution go. G prime is what makes the substitution work. The g prime factor makes the substitution work. To identify properly the g prime factor, we are going to have to identify what the inside is. So this g of x, that's the inside. Notice that the g of x on the left is the same g of x on the right. So note that the inside is staying the same. So what we're going to need to make this go is the g prime factor. What we want to do is establish a formal method to make this work. Some steps that we can follow in case we get stuck, in case we look at the problem and our intuition fails us. We can't see just exactly what we're supposed to do. This is like that algorithm that we learned for multiplication. Or this is like FOIL, where we learn first, outer, inner, last. So in case we forget what we're supposed to do, we introduce a method that we can just kind of run this through so that we can practice, so we don't get stuck. So a lot of times this is called U substitution. I use W substitution. It's like literally twice as good. It's double the U's. But if you're going to ask Dr. Google about this, you might also want to check out U substitution. Or if you ask Dr. YouTube, look up U substitution. Here's how W substitution works. So we're looking at f prime of g of x times g prime of x dx. The big idea behind substitution, is that we're going to trade all the x's for w. We're going to substitute all the x's for w. That's what we're doing. That's the game. All x must become w. In this substitution, all x must go. We have to transform our integral from a dx integral to a dw integral. So all x must go, including the dx. So here's how we're going to play this game. First of all, we're going to identify the inside. We're going to say w is g of x. Then we're going to take the derivative of this. If we're going to make a substitution where g of x is equal to w, we also have to know what the dx is going to become. So we're going to take the derivative of w with respect to x. But we're going to treat the dw and the dx as infinitesimally small things, or differentials. And I'm going to multiply both sides by d of x. This is a little bit shady, but don't worry, it's fine. So what we're actually going to write most of the time is we're going to say that dw is g prime of x times dx. So to make the dx into a dw, I need that factor of g prime. That's part of the dw. Now we have all the parts that we need to make our substitution. This is the integral of f prime. That's the function that we're actually integrating. G of x is getting replaced with w. And this whole g prime of x dx, all this is what we need to make the dw. I'm not just trading the dx for a dw. That's not how it works. I didn't say that dx equals dw. dw is g prime of x times dx. So to make the dw, I need the g prime of x. G prime of x is part of the dw. G prime of x is part of the dw. You don't just get to trade your dx for a dw. G prime of x is part of the dw. Now we can see that the substitution has simplified our lives, because the integral of f prime is just f plus some constant. So f prime is the outside function. That's the one that we're going to be integrating. So the integral of f prime is just f So we traded our integral in x for an integral in w, because our integral is easier in w. Integrate f prime of w with respect to w. That's no problem. It's just f. f of w plus c. Then the last thing that we need to do is replace the w with what we originally had. So we end up with f of g of x plus c. Just like we planned. That was good timing on the ball. So once we decide what the inside function is, we take the derivative to find the derivative of the inside. That's going to be our dw. That's the big question in our substitution. It's usually easy to identify what w should be, but we got to remember what's going to be our dw. That's the big question. This g prime can be different from what we have, but only by a constant multiple. So our g prime can only be off by a constant multiple. We can fix constant factors. We can't fix variable factors. So let's take a look at an example with actual functions. What we want to see here is that the x cubed is on the inside, x squared is there to be the dw. We had to put the x squared there to be the dw. The thing that we're actually integrating is the sine function. That's just what we get on first inspection here. We can see that the derivative of the inside is 3x squared. It's only off by a constant. So we're going to have to get rid of that 3. So we're going to have a 1/3. The integral of sine is negative cosine. So by looking at it, we know that the antiderivative will be negative 1/3 cosine of x cubed plus c. Let's see what the method shows us to do. X cubed is the only thing that's a candidate for an inside because that's the only thing that's been inside in a composition of functions. So w will be x cubed. The next thing to do is identify what dw is going to be. dw is 3x squared dx. So we look at our original integral and say we have x squared dx, not 3x squared dx. So I see this x squared. This is just there to be the dw. So we have x squared dx in the integral, but the dw is equal to 3x squared dx. It's okay that we're off by a constant factor, because that we can fix. So 1/3 of dw is equal to x squared dx. Our decision to make w equal x cubed meant that we decided that dw should be 3x squared dx. That was different than what we had, but only different by a constant. So my integral is going to be sine of w. So sine is the thing that we're going to be integrating. X cubed is w, so sine of w. And this x squared dx is all equal to 1/3 dw. I like to put my constants out in front. X squared dx is 1/3 dw. dw, after our original choice of w equal x cubed, we chose w equal x cubed. So dw is 3x squared dx. We just made a little adjustment. That means 1/3 dw is x squared dx. Our dw differed from the dw that we were given by a constant factor. But the difference between our dw and the dw that we were given is a constant factor. We can make that adjustment. Divide both sides by 3. If in this situation you say, I'll just divide both sides by x, you have to stop. You can't adjust a variable factor. Only adjust constants. Now we've got an easy integral. The integral of sine of something is negative cosine of that thing. So I'll have negative cosine of w plus c. The 1/3 is just a constant multiple. After our substitution, we should have an easier integral to deal with. We took our x squared sine of x cubed, we filtered out some of the noise, and we said this is just integrating sine. But we can't answer our question in w. We have to take it back to x. So our antiderivative will be negative 1/3 cosine of w is x cubed plus c. We can check our answer by taking the derivative. The derivative of negative 1/3 cosine of x cubed plus c is negative 1/3 times the negative sine of x cubed times 3x squared. The negatives cancel, the 1/3 and the 3 cancels, and we end up with x squared sine of x cubed. And the derivative of c is 0, so we're not worried about that. So we can always check by finding the derivative. It's like writing problem sets. If the problem set is on solving equations, you do not need to include a solutions guide. If the problem set says solve these equations, all you have to do is check to see if your answers are correct. That's why on a test or something like that, you should never write down an answer, a solution to an equation, or every time you write down a solution to an equation, you will know if you're right or not, because all you have to do is check to see that your answer fits in the original equation. So you will know that you are correct. How's everybody okay? Let's see a case where this doesn't work. when we're doing math stuff, we can't just do examples that work all the time. We have to look at examples. We have to attempt things and know when they're not working. Then it's the next level is know how badly they're not working. Think of it as cooking versus baking. Like if you're cooking and you're just stir frying a bunch of stuff, you really going to have a hard time messing that up. Like, I know I put too much of something in there. It's a stir fry, it'll be fine. Unless too much salt, then you kind of goofed. In which case, it's like, oh no, I put too much salt in. It's going to be super salty unless I dilute the salt with like just more vegetables. It's like, well, cut up some more vegetables, throw that in there, spread the salt around a little bit. You can cover your mistakes, right? You kind of cover up for it. In baking is, I don't know, maybe it's just me, but baking is way different because baking is chemistry and I was bad at chemistry. In baking, you have to be able to start looking at your dough and know if you goofed. It's like, oh no, I messed this up. You have to know when it's not working, and then you have to know how you can fix it, if you can fix it, right? So, oh, this is a mess. I think there's just too much flour. I have to put in the other stuff. I don't know if you can fix that. And you can't just follow a recipe, right? Because what if the recipe was written in different atmospheric conditions with slightly different ingredients? And it's like, oh, but the recipe said this. You can't just kind of slavishly follow the recipe. You have to know what you're doing. Ever been on one of those, I don't know if you've ever tried one of these, but like Hello Fresh or something like that, where they send you the ingredients and all you have to do is cut stuff up and kind of like stick it in the pan. They never ask you to bake anything. It's pretty much just like, oh, just put it in the pan. Or put it in a pan, then stick it in the oven. It's never like mix these ingredients and make sure you're and do baking, because that's more difficult. You actually have to know what you're doing. So let's see this one not work. The only candidate that we have for an inside is the x cubed. Your intuition right away should say this is not going to work because to make x cubed the inside, I need an x squared for my DW. So already we know that this isn't going to work. For x cubed, this is the thing that we notice. For w equal x cubed, we need x squared for the DW, and we don't have x squared. So that's what we're noticing. We don't have x squared. We've only got x. That's not enough. We are not different by a constant factor. We're different by a variable factor. Substitution is not going to work. Let's see it not work. Let's suppose that we didn't notice that it wasn't an x squared out there, or we didn't notice that it's not going to work. We're going to say w is equal to x cubed. And we're like, proceed with method. dw is 3x squared dx. At this point, our subconscious is saying, see, I told you we need an x squared to be the dw. We have an x times a dx, but we don't have an x squared times a dx. And we're not allowed, we can fix the constant. but I can't fix an x. So this x sine of x cubed is not integration by substitution. We're going to have to do something else on this one. Any questions? Let me offer an alternative to integration by substitution the way I did it on that previous example. This is solve for dx style. I personally don't like this one. I don't know why. But this is called solve. I call this solve for dx style because in this situation, after you find dw, you're going to solve for dx. That's why I came up with this clever name for it. Solve for dx style. I don't really do a lot of creative things like that. So there it is. I'm going to go back to the one where we know substitution will work. The integral of x squared times sine of x cubed dx. We're going to make the same decisions that we had before. We want to decide what we choose our w. W is x cubed. And so dw is 3x squared dx. In the previous problem, I said we were given an x squared dx, so I solved for x squared dx. In solve for dx style, we do something different. We solve for dx. Now, instead of replacing x squared dx with 1/3 dw, some students, if you don't like that, one of the reasons that you don't like that is that you have to decide some of the factors go over here and some of the factors go over here. And then you got to replace those two factors with these other two factors. So that's usually the hang up that we have. In the solve for dx style, you kind of get around that by just solving for the dx. Now notice that I'm going to replace the dx with dw over 3x squared. I think this is why I don't like this. I'm trying to get everything to dw, and here's some x's in my and mixed with my w. That's unacceptable. But the x squared is going to go away. So I initially don't do anything with this x squared. Sine is still the thing that we're integrating. X cubed is still the w. Oops. But I'm only replacing the dx with dw over 3x squared. So in this strategy, we just replace the dx. We leave the x squared because we're just replacing the dx. Then what happens is the x squared cancels out. Leaving us with the integral of sine of w dw, or 1/3 sine of w dw. So in solve for dx style, you leave all the x's running around and you hope that they cancel out when you substitute in the dx. We also want to see solve for dx not work. And the thing that needs to happen, the x squared all cancels out, is not going to happen in this example. There's going to be an x left over in our dx, or in our dw. So once again, we don't do anything with the x. We have the sine of w. This time, our dx is going to be dw over 3x squared. But only one factor of x cancels out. We are unable to trade all our x's for w's. So here's substitution not working in the solve for dx style. All x must become w. This still has an x left over that we can't fix. Moreover, if I go back to my original up here and say, well, if w is x cubed, then x is the cube root of w, that's just making things worse. Now I have sine of w over the cube root of x. So in this case, this workaround is not going to work. So that won't work in this case. I do want to bring this up because there are times that this kind of will work. But the problems are very contrived. And in the times when this works, it's because the problem was built to make this work. Good question. Comments? So you should be experts on substitution because we've done like an example, but in two different ways. And one example that didn't work. So we've had two examples of substitution, full method. So you should be experts, right? It's funny because some people will get frustrated when you start to do homework. They're like, oh, I don't get this. And it's like, oh, you've watched 4 basketball games, so you're ready to go try out for the NBA, right? And it's like, oh no, that's patently ridiculous. I've only watched some people play basketball. I'm obviously not going to be very skilled myself in basketball. Never mind the fact, and then you just throw that right out the window when you go watch someone do a couple of math problems. And you're like, oh, I don't get this. I guess I'm just never going to get this. And the reason that you want to think that, by the way, is you want to think it's physically impossible for you to understand this, because that gets you out of doing it entirely, even though it doesn't at all get you out of doing this entirely. But that's like the lazy part of your brain, the part that doesn't want to do this work, saying, let's not do this work. Oh, come on, you can't do this. This is just beyond you, right? But that's just not true. This is math. Like literally this stuff, that which can be known. That's why it's math. That's why philosophy kicked it out. All it requires is time. More dedication. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.